here is to give you some introduction into eROSITA, and in particular also into the view that eROSITA has on galaxy clusters. Okay, so that will be more like a broad overview, because I assume you're not all experts in X-ray astronomy or in galaxy clusters. But in any case, yeah, you can also feel free to ask questions at the end if something was not specific enough or so. Okay, let's see. Good. So let's say the key people and the key institutes involved are listed here on this slide. So first of all, eROSITA is an X-ray space telescope that sits on a satellite together with another X-ray instrument. The satellite is called Spectrum RG, and the Russian X-ray instrument is called ARDXC, and the German X-ray instrument is called eROSITA. And so within eROSITA, there's those institutes that are listed here on the left. They are involved. The principal investigator of eROSITA used to be, until very recently, Peter Predel from Max Planck Institute for Extraterrestrial Physics. Yeah, now that eROSITA is safely launched and working very well, he gave it over to Andrea Meloni, who used to be the eROSITA project scientist. And now Mara Salvato has replaced him, the project scientist. And then from the heads of the institutes on the Russian side, that's Rashid Sunyaev, and on the MPE side, that's Paul Nendra. And of course, there's a number of industry involved as well. Okay, so taking a look at the instrument. So first on the left is the mirrors, and we go, let's say, forward in time until some point where we actually also rewind. So here it's July 2016, when eROSITA was still sitting at MPE in Garching. And there you can see eROSITA is actually not just one telescope, but it's 7 telescopes. And it also has 7 cameras, CCD cameras, X-ray CCD cameras. The specs, or the special things about eROSITA are, it's a very short focal length. That's very good for a low particle background. It has a very large field of view, 1 degree diameter. The point spread function, especially in the survey, is about a factor of 2 better than what we had with the ROSAT all-sky survey 30 years ago, so 27 arc seconds. The other interesting thing is that eROSITA actually has a very good energy resolution, very close to the theoretical limit for a CCD. So it's slightly better than XMM and Chandra, the other currently existing X-ray telescopes. And the mirrors have the highest effective area at soft energies. So eROSITA has a very large effective area because it's 7 telescopes. Each of the telescopes has 54 mirror shells in order to get many photons per second from a given source. And the large field of view is, of course, there. eROSITA is a survey instrument, so within half a year, the full sky is being surveyed to a significant depth. The other nice thing about it is the image quality is actually very high, because you just have a single detector at the focal plane, so you don't have any ugly chip gaps or so that plug, for instance, XMM also. Okay, then let's move on. So here's January 2017, when eROSITA went on its way from Munich to Moscow. So eROSITA is sitting here, I hope you can see my mouse, in that container, and put into that plane, and then on its way to Russia. One could also follow that, of course, live. So here going from Munich to Moscow, and it was on time, only 28 minutes late. That's a very short delay compared to several of the other delays the project had suffered in the previous years. Then it was picked up with a high-tech truck at the Moscow airport so that eROSITA could be brought to the Lavochkin company. Okay, and everything worked perfectly. And then again, we move forward. Here we are in December 2017, where eROSITA is already sitting on the navigator platform here together with the Russian instrument, ART-XC. So here the black slender one is ART-XC, and the black silvery fat one is the eROSITA. Okay, good. Then again, let's move forward. Here we are already end of 2018, when the, let's say, the German delegation and the Russian delegations, they met in Moscow. And well, if you look at the faces, it seems to have been quite a sad or serious or so meeting. And there's also not a single woman, at least not on that side of the view there. But actually, people were actually quite happy because at that time, it seemed that eROSITA was supposed to launch in March, April 2019. But yeah, shortly after that, it became clear that this was not going to happen. And instead, there was a new launch date announced the 21st of June, 2019. One thing I should mention that there were basically 4 launch windows in the summer of 2019. And if none of them ART-XC eROSITA on SRG could have been launched, then there would have been quite a significant delay for the next launch window. And because some of the components would have been over their expiry date by then, it would have caused additional delays. So it was important that at least one of these 4 launch windows SRG actually gets launched. So then on the morning of the 21st of June, it was announced, no, we, not Houston, but maybe Moscow, we have a problem, we cannot launch. So instead we will use the next, hopefully the next launch window, which is 1 day later. But then in the morning of that next day, it was announced we haven't solved the problem, we need to move the rocket back into the hangar and take a look, a more close look at what happened. So then the next launch window was July 12th. And by that time, the problem was solved. But then on the morning of July 12th, another problem was discovered. So that launch date was also not used. And it was said then, well, then we launch on the next morning if we have solved the problem. And indeed, the problem was solved by then. And that was good, of course. And the launch, everything worked perfectly. Okay. So here we are already a little further. We are in April 2019 when SRG is being moved to Baikonur, where the launch is going to take place. And here you can see you actually need already a kind of a bigger plane here, and you have to open the front like this because it's not only eROSITA anymore, but it's ART-XC and the whole satellite in there. Okay, so I think that if I remember correctly, what I was told from Peter Pedel, that took the better part of a day or so to get that out and on the truck. So in here we are already in inside one of these huge halls. Again, eROSITA sitting here, ART-XC down here. The whole thing is the navigator platform, the solar panels down here, and this block DM upper stage, because eROSITA is in orbit around the L2, so someone need to get there. That's also the thing that would have gone past the expiry date if it hadn't been launched on the July 13. Now, yeah, looking at this, it almost looks a little aggressive, I would say. Like you have the phaser bank here, and then the photon torpedoes maybe coming from here. But this is all, of course, just very peaceful. I mean, it's only for science, just telescopes. So here they are already inside that, in the front of the rocket here, and there is this air cooling there because apparently it was quite hot during the day, like more than 40 degrees in the shade. And obviously here, there isn't any shade here. So you want to cool that a little bit. Okay, and then you move it towards the launch platform, and you're actually moving here from the right to the left. You can also see the little cars here and make sure that nothing goes wrong. They're also going in the same direction. And then you arrive at the pad. By the way, these images are probably from June 2019, so from the first attempt of the launch. But anyway, the second time it probably looked very similar. Okay, then you lift up the rocket until it stands there, and then you wait for the launch to happen. And so let's take a look at that. Again, launch worked perfectly. So why don't we look the same thing again from a different perspective? Yeah, this also makes clear it's probably a tough job to be a cameraman standing down there and filming the launch. And anyway, so the launch worked perfectly, and at least in Germany, that was also then in the news, the major news that we have here. But one thing that was surprising, at least to me, was, so that's again, eROSITA, the 7 telescope. There were these green rays emanating from eROSITA, and I didn't quite understand what that meant. Maybe because one interpretation could be because they knew it was an X-ray telescope, so maybe they considered you put a photographic plate behind the star, and so then you shoot some X-rays and then grab the photographic plate to see what I don't know. But I think the reason is a different one, and it's because of an animation that I'm going to show now, that this became like this. Let's see. So let's also take a look where eROSITA is now after it's been launched. Let's move a little forward. So that's a movie from the German Aerospace Agency. Okay, now. Right, so here's the sun in the middle, then Earth and the moon orbiting about Earth. And then there's the so-called L2 point, the Lagrange point 2, where the gravity here towards the left and the centrifugal force cancel each other. And that's a point in space that there's nothing at that point, of course, but that's a good point to have orbits about. A couple of other satellites have been there, and SRG is there now as well. Okay, now let me move forward a little bit. The question is, how does eROSITA scan the sky? I already said it's a survey instrument. And it will scan the full sky, and not only once, but actually 8 times within 4 years. And so, yeah, what SRG does, it spins around itself all the time. Solar panels directed towards the sun, and antenna that transmits the data to the ground has a large enough cone that well, Earth is always in the cone. Anyway, so that's the way eROSITA scans the sky. So that means after half a year, eROSITA done around half, the full sky has been scanned once. And the exposure time is not the same everywhere, but as you can see there at the poles, the exposure will be deeper or larger than in other areas. So then in the usual way, if you want to present the full sky in a 2D map, here's one way of trying to represent that. So that's then what we will hope to get, and that is what we actually have already. And I will show the map, of course. So then after, let's say, 9 months after the launch, we're over. So we need some time to get to the L2 after the launch, and you need to check out the instruments and do some calibration, performance verification observations. But then in December, the all-sky survey had started. And so in June, it was done. And then this image was made publicly available. But there's one additional note, maybe before talking a little bit more about this image. It's a Russian-German collaboration, as might have become clear by now. But the collaboration is done in the sense that the X-ray photons from the western galactic half, which is on the right-hand side here, go to the German part of the consortium, and X-ray photons from the eastern galactic part go to the Russian side of the consortium, at least initially. Eventually, I'm sure scientists will just work together for the science where it makes sense to have the full sky. But here, that is already an example where they have worked together and produced one map of the full sky. And yeah, maybe let's take a quick look at some of the things one can see. Well, first of all, you can see some of the large-scale stuff here in our galaxy. But other than that, what is, of course, most interesting when you look at the full sky is, let's say, either very bright objects or extended objects. And in our galaxy, basically, the bright objects are X-ray binaries, so neutron stars or black holes with a companion. And the extended stuff in our galaxy are the supernova remnants. In terms of extragalactic objects, the only things that are extended are either a few of the very nearby galaxies, like M31 or so, or galaxy clusters. And so that's essentially what you can see here. So this one here is SCO-X1, the brightest X-ray source in the sky, where Riccardo Giacconi got the Nobel Prize in physics for, because in one of the rocket experiments, they just happened to scan across that object and then discovered the first extrasolar X-ray source. What else? So we have the Virgo galaxy cluster, the most nearby big cluster, spanning maybe 100 square degrees or so. The Shapley supercluster, you can see some of the dots here and a few more to the experts, very well-known clusters. And then here you have the Vela supernova remnant in our galaxy, the Crab pulsar and the Pulsar Wind Nebula, so also an extended source, also left over partially from the supernovae, even though the Pulsar Wind Nebula comes from the pulsar. And more extended stuff here, and also more clusters over here. And of course, we shouldn't forget the large Magellanic Cloud down here. So yeah, quite a nicer image than the one we had before from the ROSAT all-sky survey. Maybe one more thing I should say. So you see the different colors, and blue is the hard X-rays. So one might wonder why here in the center it's all full with blue sources. That's not necessarily because they happen to be the harder sources there, but you have the neutral gas in our galaxy that absorbs the soft X-rays. So the only X-rays that go through are the hard ones. So up to, I think here we stopped at maybe 2.3 keV or so, if I remember correctly. Let me check. Sorry. Yep. Right. But eROSITA in principle is also sensitive up to, let's say, 8 keV, even though with somewhat less effective area. Okay, but here for this talk, the focus is more on the extragalactic part, and in particular on galaxy clusters. And eROSITA is, of course, also there not only to constrain dark energy, but to also to study the large-scale structure in the universe. So we know that very well from the galaxy distribution. So here's the two mass distribution of galaxies, so near infrared selected galaxies. And we, of course, we know the galaxies are not randomly distributed, but they align in these kinds of filaments and so on. And yeah, there's many galaxy clusters here marked, and also a couple of superclusters. So that we know. If we look now into the corresponding image from the eROSITA All-Sky survey, we can see basically the similar kind of objects. Some are better visible here in X-rays, others are less well visible, because, I mean, the resolution of this map here, of course, has to have been degraded quite a bit so that you can take the full sky here on this just one screen. And by the way, I marked one particular system here, the Able 339195 system. You can see over there, because that was the target of the performance verification observation of eROSITA. So I'll talk a little bit more about that one later. Oh, okay, now already. Okay, very good. So, but before going there, since not everybody may be completely familiar with galaxy clusters, 3 quick slides on what galaxy clusters are. So as the name implies, they are clusters of galaxies. So here's a Hubble Space Telescope observation of one of the famous nearby galaxy clusters, Able 1689. What you can see is, well, all the galaxies that have this kind of color here basically are part of the cluster. Other galaxies that have a different color are presumably not part of the cluster, and usually maybe in the foreground or in the background. And you also have a couple of foreground stars in our Milky Way here. You can also see some galaxies have kind of a funny shape here. That's not because in reality they actually look like that. It's just because the images are being distorted by the gravitational potential. These galaxy clusters are the most massive objects in the universe, so the gravitational potential is quite deep here, and that causes these so-called gravitational lensing image distortions of the background galaxies. So if you measure a couple of these multiple images, or statistically the small distortions, you can also determine the total mass of clusters, including dark matter. Now, if you take an X-ray image of the same galaxy cluster, this is what you see. So at first one might think these X-ray telescopes, they have really a poor spatial resolution because the emission from all the galaxies just gets blurred into one big blob, but that's not the case. Chandra actually has a better spatial resolution than most ground-based optical telescopes, so 0.5 arc seconds. So the reason is that the X-ray emission doesn't come primarily from the member galaxies, but it comes from the hot gas that fills the entire gravitational potential. And hot means maybe 10 to 100 million Kelvin or so, and it's optically thin, and it emits in X-rays. The gas density is actually quite low, so less than 0.1 particle per cubic centimeter, so basically a better vacuum than what you can create on Earth. Nonetheless, these clusters are very bright X-ray emitting sources because they are so big, so maybe 10 million light years across also. Okay, so when you look carefully So I said the emission doesn't really come from the individual galaxies, but just from the gas that fills the potential. If you look carefully, like the one up here, there is actually X-ray emission associated with that galaxy, and that is because the supermassive black hole at the center of that galaxy is currently actively accreting matter, and that also results in X-ray emission. You can also use X-ray observations to determine the total mass of clusters, because basically, so 10 to 100 million Kelvin is quite hot. So in principle, the gas would like to expand given that temperature, but it doesn't expand, it just sits there. So something must hold the gas together, and that's of course the gravity from all the mass that you have there. And there, basically consistently with the weak gravitational lensing, you find that maybe 85% of the total mass should be in the form of dark matter, given general relativity. Okay, so the last special thing about X-ray observations of clusters that I am going to mention is, so with X-rays, you see the clusters as one single object, just the gas that fills the potential. While in the optical, you see the sum of individual galaxies. Now, we think we know how structure grows in the universe, and we have seen how the galaxies are distributed in the sky along these filaments, so we know how the galaxies are distributed. In the computer, we also know, so here's an example from the magneticum simulation provided by Veronika Biffi and Klaus Dolak. We also know how the gas is distributed, and it's also expected to be distributed along these filaments, and these knots here are then galaxy clusters where the gas density is highest. But we haven't really seen these kind of filaments in emission, at least the hot part of these filaments with temperatures of 1,000,000 Kelvin or so. We expect there's no reason to think it's wrong, but we expect them to be there, but we haven't really seen them. So maybe with eROSITA, we might also have a good chance of detecting some of those filaments, or at least the very dense part between the galaxy clusters. So again, so one question for eROSITA is, does the structure in the universe really grow like as we see it in these nice simulations? In particular, the gaseous content. Another question that we may hope to address is how do the outskirts of galaxy clusters look like? Here's an example from a different hydrodynamical simulation, Mauro Roncarelli, and then we have added some relevant radii here and that overview of the clusters of galaxies and of the outskirts. And with the X-ray satellites Chandra and XMM Newton, basically you were limited to that inner circle here, which says R500, which is one of those characteristic radii of clusters. Now with the Suzaku satellite, you could basically reach here to R200, but the imaging properties of the satellite, they were not that good, like a 2 arc-minute point spread function and so on. But it was a step forward, of course. Still, there's lots of stuff going on beyond this R200, and let's say another interesting radius here is R100, which is very close to the so-called virial radius. But even beyond that, there's stuff falling in along these filaments, clumps, and so on. So that would be great, given the large field of view from eROSITA, to take a look at those systems. Here's again another comparison. So in terms of, let's say, size and where eROSITA is good for, it's the moon, so 1/2 degree across, and the field of view of XMM Newton is also roughly 1/2 degree across. Chandra is somewhat smaller. The eROSITA field of view is about 1 degree. And additionally, it can do very efficiently so-called raster scans, which is indicated by these little arrows. Here, you can scan a certain region on the sky very efficiently, something that external Newton, for instance, cannot do. And additionally, remember, all of that field of view area is a single CCD, so no gaps there. Okay. So then, given these features, let's select a cluster system for the performance verification phase of eROSITA to scan that entire system. So in the end, what we settled on was the Able 339195 system. So here's a ROSAT PSPC, or two ROSAT PSPC observations. Again, that's 2 degrees here on the side. So even with ROSAT, you could already see this kind of emission bridge here, but other things are much more harder to see there. You can also see is maybe 2 systems down here. So it's actually a triple cluster system that is in a pre-merger phase, presumably. And R500s are also marked of these systems here. Now, you might think the white contours here are the X-ray surface brightness contours, but that's not the case. The white contours actually obtained from millimeter, sub-millimeter observations from the Planck satellite. So that's a so-called Zunyaev-Zeldovich effect Y, Compton Y map that traces exactly the same electrons, but it traces them in a different way. But one can see there's a very nice correspondence. You can also see this indication of the bridge over here between the systems. Okay, but yeah, Planck also has a very poor spatial resolution, so you can, let's say, see that this is actually 2 systems down here. Now, where is that system? The 339195. That's again the 2-mass extended source map. So basically infrared selected galaxies, 500,000 of those, and overlaid on top of that is maybe 100 or so nearby X-ray selected galaxy clusters. So the first thing one notices in this map here is that with these, let's say, handful of clusters, 100 clusters, you can see the same large scale structure that you can see when you sample 500,000 galaxies. And the reason that a few clusters are enough to see the same thing is because they are much more highly biased. So you can see the same kind of superclusters, the Perseus Pisces superclusters, Hercules and Corona Borealis superclusters, and here's the Shapley supercluster. Anyway, so our system is down here. So let's zoom in a little bit. What you can see is these are the 3 clusters here. So redshift 0.05, quite nearby. There's a number of other nearby very bright galaxy clusters. And if one looks carefully, the redshifts are lower here and higher on that side. So apparently one looks down kind of a filament, very large scale filament, like in this kind of direction here. Okay, now and on the eROSITA map, where is it? I had already pointed it out earlier. Let's zoom in. So it's this system here, but now it looks different. That is because this is in galactic coordinates, so a rough coordinate transformation here into right ascension and declination that's the Able 3395 north and south, and that's the 3391. And that's an annoying star here. Again, so that's how that looks like. The system is here. So if anything, one might expect some, on a very large scale, some kind of filamentary structure going north-south or so. Okay, so what I've shown here is the eROSITA All-Sky survey data, which was finally obtained in June. Now we go back to October 2019. when eROSITA saw the first light, and shortly after that, or actually quite close to that time, part of it was, you can see what was actually the first light observation, the performance verification phase, where this galaxy cluster system was observed before the all-sky survey started. And here's actually where the data are just coming in from the one of the scan observations, and I just happened to be there at MPE, which was very nice. So could go to the control room and saw live how the data are coming in. Quite happy, of course. So that's the resulting image, and I'm going to show a couple of images, and I'm trying to show also, first of all, make clear what one can see here. And on the other hand, trying also to make clear why this is, let's say, fascinating for us that work on X-ray galaxy clusters, by showing what was known before, or what one could see before. So first of all, yeah, there's galaxy clusters in here. So that's the AIfA 3391 and 3395 north and south systems. And that's, again, that's not a galaxy. That one consists maybe of 1,000 galaxies. Just in X-rays, you see the whole cluster is a single object. Then you have lots of these little dots here, and almost all of them are, so hundreds of them, all of them, or almost all of them, are supermassive black holes that are accreting from their surroundings. So it's all galaxies that you see, but this special kind of galaxies that have an active supermassive black hole at their center. Okay, then you see something else, something disturbing. Again, that's the bright star, that's Canopus. That's the second brightest star, optically brightest star in the sky. And that caused actually a couple of issues. Not because of the X-ray emission of that star, because it's an A-type star, which is intrinsically not that bright in X-rays, but because of the optical UV photons that leak through the X-ray filters. If you have such a bright optical object, the filters can be as good as they want. There's a few photons that always leak through, and then they are incorrectly assigned as being X-ray photons. And there are so many of them that we actually lost some data when eROSITA scanned across here. There were so many events that, that the telemetry would have been saturated if they were all transmitted. So there was a mode where automatically all the events are discarded and not transferred to the ground. So we lost some exposure here, and in the second scan, we did it somewhat differently, that there was less loss. Okay. What you can also see is, sometimes these galaxy clusters don't just sit there on their own and wait for something to happen, but sometimes actually merge with other galaxy clusters. And that one example is these two here. They are not just projected the similar position on the sky. They are at the same redshift. So they are involved in some merging process there. And then something that you can not very well see in this representation, but there is actually some emission bridge that you can see. In some of the other images, you can see it better. And that leads us to one of the bigger riddles. So we know that there is dark energy, but we don't know what it is. We know there's dark matter, but we don't know what it is. We know how much baryons there are, so normal matter in the universe, but we don't know where they are. At least for half of them, we haven't seen them yet in the local universe. But based on the numerical simulations, we expect them to be in these filaments. But they are just hard to see because the density is low, and with 1,000,000 degrees, it's just a temperature that is also not great for emission. Now, the hottest and densest part of this so-called warm-hot intergalactic medium is expected to be between such cluster systems. And that is maybe what we are seeing here. It's not completely clear because, I mean, the system has been observed before with Chandra XMM. I show the observations soon. But mostly hot gas has been found and not a million Kelvin gas. And so one possible interpretation is, and that's what the authors also did, is that the gas that we see here is basically just cluster outskirt gas that has been somehow tidally stripped, and that makes that bridge here. So it's not a true primordial filament. But also that we want to check with eROSITA, because eROSITA has this very good soft response where we can see this cooler gas much better than Chandra XMM can do that. Anyway, so that's where, like say, these kind of filaments here, you expect that much of the normal matter in the universe is contained, and we would like to actually confirm that. You can see something else. Take a look at the time. Oh, okay. Okay. What you can also see is some of these fuzzy clumps. You not only see the little points, which are the AGN, the supermassive black holes. Some of the sources are kind of fuzzy, and these are not AGN, at least not only, but these are other galaxy groups at the same redshift that are falling onto the system, or just background galaxy clusters. And more than half of the ones that are pointed out here are actually background clusters, as it turns out, but the others are not. And this is some, and you can see if you run the software across that, you see actually maybe 50 or so of these extended blobs, while with let's say SPT and ACT for the specialists here, so Sunyaev-Zelevich effect surveys, they see basically 3 clusters here in that same field together. So you can see the power of eROSITA of not only finding the high redshift clusters that ACT and SPT have found in the field here, but also these lower mass clusters at lower redshift that you can't see with the current generation of the SZ instrument. So more than 50 or so. And this is something that hasn't really been seen before like that. Many of these clumps are actually at the same redshift. So you can see exactly what you see in the simulation, these clumps that are falling onto that main system here. So that, again, is something that hasn't really been seen in that clarity before. Okay, then what has been seen before is this one here. That's an image from the ROSAT All Skies survey. You can already see here this kind of emission bridge, but on the other hand, the spatial resolution was poor, very few photons, so there is a difference to this, let's say, wavelet filtered image here from the eROSITA data. I mean, the difference is obvious. Also, XML Newton had observed the system, but since the field of view is so small, you only see the central part. You see the central part, let's say, equally well, one could say. The same kind of AGN are there, except maybe a few that weren't there in the past or are not there anymore, so they are variable. But essentially, in the central part, you can see very similar things. Now, the exposure time needed for eROSITA to make this image is comparable to the exposure time XMM needed to make this image. So again, you can see the advantage of eROSITA. You can see all the big stuff and simultaneously also the good spatial resolution. Another image here from the Planck satellite and the Sunyaev-Zelevich effect. Again, you could already see the bridge here, but for instance, as I showed before, can't even resolve these 2 southern clusters into individual components. Okay, so that's why we think that there's really some progress just from the visual impression already. Oops. And here's 2 more or 3 more visual impressions of the same system, and I'm actually getting very close to the end, as I should be. That's a 3-color image of the same cluster. So blue is hard X-rays and red is softer X-rays. And here's another representation and a wavelet filtered image that is, let's say, tailored so that you can see the emission bridge better here, and also some of the other clumps in the vicinity. Now, since we made these images, of course, we have continued to work on the data, trying to use all the data that we have here. Of course, for these kind of first light images, we only use the, let's say, the best safe parts of the data. Now we have also gone back to try to make use of the full data that we have from the scan, and that's this representation here. So you can maybe go back and forth. So here you can see, let's say, these couple of clumps. And here you can see that the field of view is already much bigger, again, taking all of the scan data. And you can see it looks a little funny, like this range here and this range here. This is just eROSITA in total did 3 scans of the system and also 1 pointed observation here in the center. And that's why the outer parts look like they look like. But again, you can see many of these fuzzy clumps here everywhere, and this is also not an artifact. That's another big galaxy cluster down here just outside the field of view. So what we are also doing with these kinds of images, trying to look for other filaments. So of course we clearly see this emission bridge here, but maybe we see also some filaments in other direction, and we think we have found some filaments that make sense and that are hopefully significant, but we are still working on checking the significance, so I'm not going to show where we think they might be. Okay, so let me maybe close on this by showing a slide also from Andrea Meloni, where he lists at least a good fraction of the people have been involved in on the eROSITA side. So thanks a lot.
Thanks a lot, Thomas. That was really interesting. We already have a few questions, so I'm just going to read out some of them. Okay, so the first one is from Boom. So he's asking, do the 7 mirrors work together like the phased array feed of a radio telescope that is providing multi-pixel and wide field of view mapping while improving the angular resolution at the same time?
Mm-hmm. No. They work as independent telescopes. So each of them is its own telescope, its own detector. So basically you get 7 times almost the same image from almost exactly the same area in the sky. So what you gain there is, by combining them, you don't gain spatial resolution, you just gain photon statistics, that you have 7 times the photons. In detail, it's actually not 7 identical telescopes, it's 5 and 2 identical telescope detector systems, because the filter setup differs a little bit, but it's a small difference.
Okay, thanks. So the next question is from Hartmut. Is there a plan to publish a publicly available eROSITA point source catalog? And if so, when is this expected to come out?
Yes. So that can only be answered for the, let's say, Western galactic half, so for the German part of the eROSITA sky. And but at least for that, it's very clear. So the first data release, which actually will not only include catalogs, but also the raw data, is expected to occur early 2021. So in less than a year, much less than a year from now. Well, actually more like half a year from now. But that will be basically the calibration and performance verification phase data, like the one from ABEL 339195. But also the so-called EFETS data set. That is a mini survey that eROSITA did of maybe 120 square degrees or so. And it's a contiguous field, so it's basically the largest, even though it took only a few days to do, the largest contiguous X-ray survey to this kind of depth that exists today. And let me try to remember. So in that field, for instance, 400 galaxy clusters have been detected. And how many point sources? Before I say a wrong number, maybe I don't say a number, but of course a large number of AGN and a large number of stars in our galaxy. So it's expected that maybe March 2021 for these 120 square degrees, the catalog and the data will be made publicly available. Now then the next step will be the all-sky survey data, at least from the western galactic half. So that is expected to be made publicly 2 years after the first all-sky survey was finished, which was in June. So maybe June, or let's say July, August 2022. That's the expectation. And then, roughly speaking, every 2 years, another release of the subsequent all-sky surveys.
Okay, thank you. Next question is from Majid. How are the images from the 7 CCDs combined within the telescope or back on Earth?
Back on Earth. In fact, yes. So basically, we get let's say one table for each camera, where let's say each photon has an entry. So you have a camera, you get an image, but the special thing with X-ray astronomy is for a photon, you not only know where on the camera it was detected, but also you know precisely when, and you have a rough estimate of the energy of the photon as well. So that doesn't work with the optical photons. So basically the typical way that the data is handled is basically you get a table that for each photon you get a line, a row, that has the position, the time, and the energy. And then for each of the 7 cameras, you get that table, and then you have software on the ground to combine them in the way that seems most useful.
Okay, thank you. There's another question from Arun, but I think Injay had his hand up, so I can see. So Injay, can you unmute and ask your question, please?
Yes, so very interesting talk, and I just want to mention that in term of the filament, that we have done work. I mean, Tanimura, myself, and Gary Hinshaw, and various other people, of stacking the luminous red galaxies from the Sloan Digital Sky Survey data, and then on the Planck Compton-Y map, and we saw like around 5 sigma detection of the accumulated filament, you know, from this 10 megaparsec region connecting the clusters. Although we try other catalog later, I mean, Dennis tried the other catalog later, but we didn't find such signal. But it looked like by using that stacking, one can actually having a aggregate signal of the filament. So I mean, I'm actually quite looking forward to the eROSITA release, so that we can try that on the other Compton-Y map. Yeah.
Yes. Yep. Very good point. Yes. So there's a couple of works who do this kind of, let's say, stacking techniques with apparently quite promising detections of the WIM filaments and in this statistical way. And indeed, that is also planned to be done with the eROSITA data. And of course, on the other hand, you can also then use, by knowing where the clusters are from the eROSITA data, you can use other data to try to find the filaments in between, like maybe from Planck and so on. So that's of course one approach that is very useful to try to confirm that the hot gas is really in these filaments. The other approach is to actually look at individual systems to see if you can really directly see in one system, yes, the filament really goes like this as we see that in the simulation. So it's kind of an approach that at least in principle could be even more convincing if you can see that directly one picture and compare it directly to what you see in the simulations.
Yes, indeed. I wonder, so the latter thing which you mentioned, directly see the filament, is just applicable for these X-ray images, right? Because usually for the Compton-Y parameter map, the signal to noise ratio isn't high enough to allow us to see that individual system. So that's why we use that aggregate method. I don't know whether the future CMB state 4 would allow so, but so far the Planck certainly can't.
Yes.
Yeah.
Mm-hmm. It's also very challenging with the X-ray data, and it's not completely clear yet for, let's say, how many systems we will succeed in actually seeing them. Because, I mean, in the all-sky survey data, the exposure is not that large, obviously. Like this performance verification observation that I showed you from the 339195 system, the exposure there is larger than what you will have over the sky after the 4 years of surveys. So the exposure is maybe between 10 and 15 kiloseconds or so, roughly, at least in the central region, while it will be quite a bit lower for the all-sky survey. So it's not clear yet. I mean, it's very challenging to see that on individual systems in the X-rays. But I mean, after the 4 years of surveys, there will be another phase of at least 2.5 years where people can propose, everybody in the world can propose observations. And if you think it's useful, we could target some of the other nearby galaxy cluster systems more deeply with the raster scan and trying to identify some more of the filaments that we think we might be seeing in the 339195 system. So in X-rays, it's also very challenging.
Thank you. Yeah.
Okay, thank you. So we got 3 more questions. So Arun is asking, from your observations, do you hope to get information about the nature of dark energy or its equation of state? Yeah,
so now, if I had 10 more minutes, I would show you the remaining 10, 12 slides that I had put right here after this slide starts. But I'm not going to do that because my time is up. So the main science driver for eROSITA is indeed to study dark energy. And I know that I mentioned in the abstract that I will talk about dark matter and dark energy, and I haven't talked about dark energy yet. So let's maybe use 1 minute at least.
Yep.
The main science driver is to study dark energy by detecting about 100,000 galaxy clusters. So at the moment, we know maybe on the order of maybe 2,000 or so galaxy clusters from their X-ray emission. And eROSITA will add another 100,000 to those. So obviously, from the statistical point of view, we will have plenty of clusters, clearly enough to constrain dark energy very precisely. But what you need is not only the numbers of clusters, you also want to have a very good mass estimate of clusters, and that's a little harder to obtain very accurately. So for that, we plan to use reglensing measurements. In any case, so the forecasts are for eROSITA based on let's say a Fisher matrix forecast that we did maybe in 2018 with Annalisa Pilipich being the first author, that we found that clearly eROSITA should be considered as a stage 4 dark energy experiment. You may remember in 2006 or so, there was a dark energy task force in the US who were tasked to provide a report, which are the next instruments that help us understanding dark energy. So they had these 4 stages from 1 to 4, and 4 the best ultimate ones. And given those criteria, eROSITA is really a stage 4 dark energy survey. So the expected constraints on the equation of state of dark energy are pretty tiny. I can also dig out
I just wonder, you might mention that these 100,000 or even more clusters and constrained dark energy. What statistical method are you plan to use to do that? Do you use like a cluster number count or like a correlation function? What is the most effective way to extract that information. Yeah.
Yes. So based on our forecasts, we identified that at least with the knowledge that we had at the time, that the so-called cluster mass function is the best, the most powerful method. So the mass function, what is that? That is similar to number counts, or basically it is number counts. You count all the clusters in a given redshift range and in a given mass range, the number density. And then if you sample a large enough redshift range, and eROSITA will also find several hundred galaxy clusters above redshift 1. So it does sample enough redshift space. Then from the evolution of this cluster mass function, that depends sensitively on the nature of dark energy, so the equation of state of dark energy. So that is the main method. But as you correctly point out, the correlation function or power spectrum is also powerful. And maybe for some cosmological parameters, it might even be as powerful as the mass function. So in some earlier forecasts that we did with Annalisa Pilepich again in 2012, we also forecast how well eROSITA will do in constraints on primordial non-Gaussianity. So the so-called FNL parameter, and there it actually did well. And the power spectrum correlation function had quite a significant weight there. There's other, let's say, secondary methods one can then discuss, but clearly the mass function is the most powerful method according to our current expectation. And then the second best one is probably the correlation function. Eventually, we will, once we have enough spectroscopic redshifts for the clusters, of course, there's also a plan to do the baryon acoustic oscillations with clusters.
Okay, thank you. We'll just take these last two questions. So this is Benny. What is the minimum significance X-ray photon has to have to be considered good enough to be taken as a data point by a telescope?
That's a very good question. I think probably the underlying question there is starting with what kind of significance do you consider a clump of photons a source, like an AGN or a cluster and so on. Indeed, that's a good question. Typically, for an AGN, maybe you need maybe on the order of 10 photons or so. For galaxy clusters, you may need on the order of 50 photons to recognize the source that it's actually extended. But these are just very rough numbers, at least for the galaxy clusters. It depends on how extended they are, because the bigger they are, the more background photons you have in that area as well. On the other hand, the bigger they are, the easier, I mean, it is to recognize them that they are larger than the point spread function. So it's actually a very complicated thing to directly or very clearly understand the selection function, at least for the galaxy clusters. For the AGN and stars, it's easier than for the point sources. But yeah, to give you a rough number for the point sources, maybe 10 photons, and for the clusters, maybe 50.
Just the same question. I wonder if you have a more sensitive camera, would you able to register more photon for the same object that you're observing?
Yes, but not by much. So the quantum efficiencies of these CCDs here is almost 100%. So well, it depends on the exact energy, but the quantum efficiency is just very high. So the cameras are not really the limiting factor. It's if you had, let's say, either bigger mirrors or more mirrors, then you would get more photons. But the cameras, I mean, they are just very efficient.
Oh, interesting. Yeah, that's it. Indeed, different than the radio astronomy or optical astronomy. Indeed. Yeah.
Okay, thank you, Thomas. So the last question is from Viral. Have you detected shock between A3395? How can we differentiate accretion shock from merger shock?
Well, that is a very good question. Maybe the short answer is we are still working on the spectral analysis. I haven't shown any spectra or any temperature measurements yet from eROSITA because well, we are still working on those. So, and that's why we haven't seen any temperature jumps yet, which would be one of the signatures for shocks. But we will be looking for them. In terms of surface brightness edges, which would presumably correspond to density jumps, which could also be used to identify shocks, we have discovered a couple of those, especially among the clumps that appear to be infalling to the system. And even for this, for instance, some of the clumps there that are outside or way outside the virial radius of the system, there already seems to be some interaction happening with its extremely outskirt gas or maybe even the filament gas. So in that sense, yes, we have seen some indications, but that needs further study and confirmation. And then the second part of the question was, how can we differentiate between accretion shocks and merger shocks? The example that I just gave already indicates maybe the general distinction that you have. Let's say you have a galaxy cluster and then it accretes matter, you have the accretion shock around it, versus you have two galaxy clusters colliding and then a shock in between them. If you look at these clumps falling in, that can be considered accretion, but it can also be considered merging. So it becomes a little blurred there. What is an accretion shock and what is a merger shock? To really find the typical accretion shock in temperature at these maybe 2 times the virial radius without having a big subclump falling in, that will probably be very difficult also for eROSITA. Because well, you need very detailed observations of maybe nearby systems, so that the survey data will probably not be good enough for these very detailed investigation where you need lots of photons.
Thanks a lot, Thomas. I guess there's no other questions. I can't see anything. Yeah, so I think, yeah, we can call it to an end. Thanks a lot for this brilliant talk and for this very engaging discussion session.
Thank you very much.
Thanks a lot, everyone, for joining. Okay.
Bye.
Okay. Bye.
So have a good weekend, everyone.
Yep. Bye.
Okay.